Okay, so now we're going to take a look at another way that we're going to be able to do this. I'm going to, I might as well use this problem right here. Assume that blood pressure readings have a mean of 120, a standard deviation 8. What blood pressure would you have to exceed to be in the highest 10% of this population? Whoa, something got twisted around here. Let's see. I'm going to get another fresh page here because I really want to draw this one out. Oh no, I don't have any more. Actually, I don't. I can draw my own. Okay, I'm going to draw my own. Okay, here's my standard normal distribution. See if I can do this without making it too ugly. Oops. Okay, not perfectly normal, but here's my mean is down here somewhere. My mean and my standard deviation. Okay. Percentage of elementary school teacher has a mean salary of $32,000, unless they'll use blood pressure. Blood pressure readings have a mean of 120, and they have a standard deviation of 8. Right, means equal to 120, standard deviation of 8. Assume that blood pressure, okay, so what do we have to find out? What blood pressure would you have to be in the highest 10% of this population? Okay, so now, if I drew this graphically, the highest 10% of this population, what would it look like on a normal distribution for blood pressures in this population? Well, it would look something like this. I'd be looking at these people that are in this end of this distribution, right? What did I say that area was? 10%, right? What's the area below it? 90%. So I want to find out what blood pressure do you have to be in the highest 10%? Anybody want to propose a way to do that? Yes. We need to know what the Z of that is, don't we? Right? We need to know what's the Z score for that value, because then we can kind of calculate that value. Well, let's take a look. That means that we need to find the area that's represented by 90% below or 10% above, because it's going to be the same Z score, right? That's the same Z score. Okay, so let's go to either one of our tables. I'm going to go to this table. If I'm going to this table, what area am I looking for? I'm looking for 10%. So I'm going to scan through here, and I'm going to look for the number 10% in the area portion of this, right? So let's see, 9%, 9.34. The closest one I get is this one right here. You guys see it? 0.1003. That area represents 10% above that Z-score, right? So what is that Z-score? It's 1.28. So that Z-score for that point is equal to 1.28. Now, how do I convert that back into a real blood pressure? Remember that formula? Z is equal to X minus mu over sigma. We know what Z is now, right? 1.28. Right? We know what mu is. We know what sigma is. The only unknown there is X. Right? So what does X turn out to be? Let's see. We can cross multiply, right? X minus 120 is equal to 8 times 1.28. Right? I'm going to subtract 120 from here and add it to here. So what's X equal to? Anybody got a calculator? Do that quickly. Let's see. I'm going to do it with you. 1.28 times 8 plus, looking like you're right, 120 is equal to 130.24. Okay, so that's only three significant digits, so I'll just call it 130. Okay. So people who have a blood pressure of 130 above are in the top 10% of the population. See how we use that same table to go the other direction, to tell us what the z-score is, which is the number of standard deviations above the mean. And since we know the standard deviation, we know how far above the mean that is. So we can go either way. I want to show you one more thing here, and that is, let's say I had asked for, let's say if I had asked you, well, what percentage of this population has a blood pressure below 130, right? From this area to the south. You don't have the table with you, but you're not connected to the internet. That you have your computer with you. You can go into Excel. I'm going to open up Excel. Open up a new spreadsheet. I'll blow it up a little bit so we can see it. Okay, I'm going to go even bigger. Okay, so in Excel, we have functions that will tell us that normal distribution, that store that normal distribution table. I'm going to type one in, equals norm sdist. Now, just so you know, you're going to see a lot of things come up here. As I type in norm dist, you're going to see norm.dist, you're going to see norm.inverse, norm.s.dist. Newer versions of Excel, when I say newer versions of Excel, I'm going to date myself. That might be from, like, I don't know, 1990 on, newer versions of Excel, right? Use this little dot to indicate, make it a little bit more descriptive. But it will just, in most cases, it will just take norm dist, right? And if I put parentheses in, it's going to ask me for information about this. Norm dist, it's going to ask me for X, the mean, the standard deviation, and this word cumulative, right? So I'm going to go ahead and fill that in for this. Okay, X was, what was X again? I was looking at 130, right? Comma, the mean, what was the mean? 120. Comma, standard deviation was 8. For true, when you put in true, it's going to give you, what this is going to return, I'm going to give it away. What it's going to, this is a spoiler, what it's going to give you is the area from that point to the left down, right? So if you imagined it as a table, it's giving you the area from whatever that z-score is to the left, always. We're going to put in true here because we are telling it we want that area from there down. If you put in false, it's only going to give you the probability for that exact number. And since we're dealing with a discrete number, just that number 130, it's not going to have much meaning for us, right? Technically, it's going to have it'll have some meaning for the program and for the numbers. For us, we really are looking for areas, right? So I'm going to always use true in this particular case. I'm going to hit enter, and it tells me that area is 0.894. That area to the left of 130. Remember, it was really 130 point something. That's why it didn't come out to exactly 90%. So instead of using the table, I can use Excel to tell me what the area in this distribution. In this case, I used the number I'm interested in, the mean. I didn't have to worry about what the z-score was. If I know the z-score and I want to use it exactly the way as I use the table, I would use equals norm sdist. You could put the dots in there if you want, norm.s.dist if you want, don't need to. Equals, now, I'm sorry, parentheses. Now this time, it just wants to know what the z-score is. And what was the z-score? It's 1.28, right? 1.28. It's going to give me the area to the left of a z-score of plus 1.28. And it's 89.997 and so on, right? So we just did exactly what we did with the table with Excel. Yes?
When you said that, how do you know, was it programmed to the left already too? You just know
it's always, yeah, that's always going to tell you to the left. Okay. And the other one will always tell you to the left if you put in true. It won't ever do to the right. Okay. And if I wanted the area under the distribution to the right of 1.28, I would have said 1 minus this. That would be equal to 1 minus this value, which is going to be about 10%. Okay. So we have a number of tools that we can use, a whole bunch of different versions of the Z table. Yes? Yes. I use the first one I use equals norm, norm dist. Yeah, norm, that was norm S dist. There's an S norm. That's the standard normal distribution. That's what that S stands for, standard. And standard means that it assumes a mean of 0 and a standard deviation of 1. That creates that table, right? That table is based on an imaginary normal distribution which has a mean of 0 and a standard deviation of 1. So you always get just these percentages. Yes?
So what you said about the false, like what if you put the false instead of true?
I'm sorry?
What will happen if you put false instead of true?
Oh, false? Let's do it. You can always do it. I mean, let's see. Escape. Let me get in here. That's this one. False. You'd get a number. See that number? That number represents the population density at that point. It really doesn't have a meaning for us. In other words, what it's giving you is, try and imagine you have that normal distribution, and it's giving you the probability for that one line of people that are exactly that value. And it really isn't even giving you that. It's a little bit more complicated than that. But it's not giving you anything that will be useful to you.
I thought it would be like 1 minus 2.
No, it would be nice if it was, right? No, but it doesn't. Now, we do use that false and true thing when we move on just a little bit. The next thing we're going to talk about is a special kind of distribution, the binomial distribution. This is a binomial distribution is also involves probabilities and chance and so on and so forth, but it focuses on results that can only have two values, like true or false, yes or no, succeed or fail, and so on and so forth. Okay, and we're going to get a look at a couple of examples of that. Okay, let's see if I can't find one. Let's see, two-time probability. Okay, binomial distribution. I'm gonna open up Excel again. Okay, I'm gonna get a new page. Okay. Okay. So now we have a problem. That problem asks us, study indicates that 10% of nursing home patients are diabetic. You randomly select 10 patients. What's the likelihood, and I'm gonna ask you just theoretically, what's the likelihood 10% of patients are diabetic? Probability of any individual patient being diabetic is 10%, right? 10% of the people are diabetic. You randomly select people without looking, and chances are 1 in 10 that person is going to be diabetic. What's the probability that you select 2 people and both are diabetic? 0.1 times 0.1, right? Which is 0.01, 1 in 100. What's the probability of you select 10 people and all 10 of them are diabetic? 0.1 times 0.1 times 0.1 times 0.1 times 0.1, and so on and so forth. Pretty easy to do. What's the probability you select 2 people and neither of them are diabetic? Well, probability of the first person not being diabetic is 0.9. Second person, 0.9. So the probability of both of them not 0.9 times 0.9. Same thing with 10, and so on and so forth. Easy. Long as it's like the same outcome for everybody, it's easy. What's the probability of selecting 10 people and getting exactly 3 of them that are diabetic? Well, now all of a sudden we got a million possibilities. We have the possibility that the first person is not, second is yes, fourth is no. We have a lot of ways we can get 3 out of 10 that are diabetic. In fact, in your lecture, you actually saw a formula that described how to calculate all of those different possibilities. You guys remember that formula? Right, there it is, binomial formula. Right, n is the number of the 10, x is the number 3, the number of successes, p to the 10, and p to the and q to this, and so on and so forth. That's going to be a real pain in the butt to figure out. Right, factorial would be like 10 times 9 times 8 times 7 and and so on and so forth. And then you got to take a number to an odd power and so on and so forth. This is difficult. This is going to be difficult to figure out. Excel has this formula built into it. It can help us calculate these probabilities. And the function that it uses is, mysteriously enough, binom dist. Okay, I'm going to pull it up in a second. Okay, and I'm going to use this example that we were just talking about. I'm going to put 0, 1, 2, 3. You could actually tell it to do a series here, so you don't have to do it like me one at a time, but it's easier for me to just get this out of the way. 10. Okay, let's say you select 10 random nursing home patients from this population. 10% of them are diabetic, right? Okay, so what's the probability that none of them are diabetic? We already know that that's 0.1 times 0.1 and so on and so forth. But what's the probability that 3 of them are diabetic? Well, we have a tool I'm going to do this, in fact, equals binom dist. Parentheses, again, there's a binom dot dist, but it's really the same thing. It comes up asking me for, and if you're looking at it on yours, I'll read them to you, but it prompts me for number S, trials, probability, and cumulative. Okay, so let's see. Number S, that's the number of successes. In our case, we're looking for people that are diabetic. So if a person is diabetic, that's a success to us, right? Not good for them, but it's a success for us, right? So the number of successes is 0, right? We want the probability that none of them are diabetic, comma, the number of trials. How many people are we sampling? 10. Taking 10 trials, 0 successes out of 10 people, comma, what was the probability of being diabetic? 0.1, comma. Now, again, it asks me for cumulative. In this case, I'm going to say false, because I want only the probability of exactly 0 out of 10. I'm going to hit enter. The probability of getting no diabetics out of a population that's 10% diabetic, if you have 10 people, is 0.3486, so on and so forth. If you work it out, that's 0.9 times 0.97, 10 times. That's what you get, believe it or not. Okay, you don't have to believe me if you don't want to. Okay, you could do it, but that's what you get. So that's the probability of getting exactly 0 out of those, right? So now, what's the probability of getting exactly one person that's diabetic? That's going to be the most likely outcome, right? Because you figure 10 people, 10% diabetic, most likely outcome is going to be one person. So I'm going to give that a try. Binom dist. Parentheses. And again, successes is 1, trials is 10, probability is 0.1, and cumulative is false. Again, I want it only for this probability. Up, see, it's a little bit higher, the probability. What's the probability of getting 2, exactly 2? Do you think it's going to be higher than 1 or lower? It's going to be lower because you would only expect to get 1. Equals binom dist. Probability of getting exactly 2 out of 10, 0.1, comma, 0.1, comma, false. And sure enough, probability is going down. Actually, what I'm going to do from this point on is I'm going to say equals binom dist, parentheses, and instead of putting number S, I'm going to click into the 3 over there, comma, 10, comma, 0.1, comma, false, again, still false, because I only want it for exactly 3 out of 10, and hit enter. And the reason why I did that is because if I can click into that box and hover over here, I can copy, whoops, I missed. I can copy the formula down to the rest. And there's all the different probabilities for exactly 5 out of 10. And look, 10 out of 10 is vanishingly small. 0.1 times 0.1, it's 10 to the minus, it's basically 10 to the minus 10, right? It's vanishingly small, that probability. Okay, what if I ask you what's the probability of getting 2 or fewer diabetics if I select 10 people? What would you say that's equal to? Was it 19% for 2, 38 for 1, and 34 for none? It's going to be the sum of those. Sum of all of these numbers. Probability of getting 2 or fewer diabetics is 93%, 92.9%. Everybody okay with that? What's the probability of getting 4 or more? It's the sum of the probability of getting 4, 5, 6, 7, 8, 9, or 10 out of 10 diabetics. Only about 1%. Okay? So what I'm doing here is I'm taking advantage of Excel, doing this calculation for all the individual probabilities for me. Well, let me ask you this. Wouldn't it be convenient if I could just ask it for that from the very start? Okay? If I add up all these probabilities, what do you think it's going to add up to? Should be obvious.
1.
Right. There you go. 1. There it is. Adds up to 1. That's all the possibilities. If you sample 10 people, you got to have 0, 1, 2, 3, 4 diabetics out of it. Okay. Now, in fact, you can use this binom dist function to do that. Binom dist parentheses, and now I'm going to tell it binom dist for two diabetics, comma 10 trials, comma 0.1 probability, comma true for cumulative, and it actually does calculate the probability for 2, 1, and 0 all added together. That's the difference between false and true for this function for diabetics. Okay? If I used true this time, so true tells it I want the cumulative probability for 2, 1, or 0 diabetics out of 10. In other words, all 3 probabilities added together. Just as I did here, I took the sum here, I got the same number by doing the same thing with just putting 2 in. Okay, so if I wanted it to calculate for me the probability of 3 or more, what would that be? Diabetics, if I sample 10. Okay, I know what the probability of 2 or fewer is. What's the probability of 3 or more? Bingo, 1 minus that probability, right? 7%. Okay, one more thing. What's the probability of less than 4? Equals binom dist out of 10. What's the probability? What should I put in there? What should I put? First, for number of successes, what should I put? Less than 4 diabetics out of a selection of 10 randomly selected people. What should I put in there? If I put in 4, it's going to count the four part, right? So it should really be 3, comma, 10, comma, 0.1, comma, true, right? This is the probability of getting less than 4 diabetics if you select 10 people, right? 98%. Okay, so it's a little bit of a word problem, isn't it? Yes.
Again, stupid question, but the true again too quickly.
I'm sorry?
The true one, when you put the true in.
When you put the true in, it gives you, for instance, if I put 2 for the number of successes, then I put true, it gives me the probability of getting 2, 1, or 0 diabetics. All 3 probabilities added together. Okay. If I put false in, it would only give me the probability of getting exactly 2 out of 10 people that are diabetic out of the 10 people I selected. Okay. All right. So there's a homework assignment up. I may put the wrong due date on it. It's actually due a week after the test. I put it due for the night of the test. I'll correct that. But to tell you the truth, probably wouldn't hurt to work on it anyway. Okay, but you have that extra week to hand it in. Now, sometime during the week, or most likely maybe on Saturday or Sunday morning, I'm gonna set like an hour aside and like do something online, like go over the 2 homeworks maybe, so that like if you had problems with any of the problems on the homeworks, that you'll have a chance to let's see me work through either the actual homework from last week or maybe some simulated versions of it that are very similar in this week. Yeah. Okay. So I think that's it. Probably calling it a night. Questions?
Yeah, so if you want to do if true is below, if you want to get 9, would you just write true and then do 1 minus?
That would work, wouldn't it? No, that would give you the probability of getting exactly. If you had done,
If you did true,
hang on, if you said binom dist,
right?
comma, 9, comma, so on and so forth, and said true, it would give you the probability of getting 9, 8, 7, 6, all the different outcomes below 9, including 9, right? So if you said 1 minus that, it would then give you only the probability of getting exactly 10. That's the only thing.
What I mean. So it would give me, so if you wanted, say, probability of above 8, then I could do 1 minus and then
1 minus what?
1 minus binomial disk 8.
That would give it would include 8. That would be then 9 and 10 only. If you wanted
If
8,
you wanted it above 8.
if you wanted above 8, yes,
8.
that would work. That would work. If you didn't want to include 8, above 8, you just wanted 9 and 10. You'd put 7 if you wanted 8, 9, and 10. Yeah. Yep. Okay. I mean, these are really kind of word problems, right? I mean, you just got to kind of sit there and not get flustered, not get confused by them, because the operations are really pretty simple. So we learned about z-score. We learned about standard normal distribution. We learned about how to view it, how to approximate the areas that we're looking at, how to actually calculate more exact areas using tables and using functions in Excel. And we learned about the binomial distribution. The only thing we didn't learn about was the Poisson distribution, which is, I don't think we covered that in the lecture, so I'm not going to bring that up and confuse you for the test. Right? I don't think we're going to have that. No. Yep. Okay. We'll talk about that briefly maybe next time, just so if you ever run into a problem, you can anticipate. It's kind of like the binomial distribution. Okay. Good. Anybody ever been to the Hall of Science in Queens here? Right. They have a demonstration of a binomial distribution where they have like a little ball dropping on pegs. And as it comes down, it hits the first peg, it could go either to the left or the right, and then it hits the second peg, and so on and so forth. It goes down about 20 pegs. So you have 20 trials of 20, and you can have so many left turns and right turns. Of course, the most common outcome is the middle, right? Half and half, right? And then less and less likely to get those other outcomes as you go along. And if you look at it, it actually forms an approximation to the normal distribution, just like we were talking about. I'll show a video of it. Yes. Right, exactly. That's right. It'd be a perfect binomial distribution.